mushroom cloud snakes skyward, hurling the atom's deadly radiation high into the heavens.
I brought some barium hydroxide octahydrate and some ammonium nitrate, and I'm going to combine them. So that must be the barium, doesn't smell. Ammonium compounds smell. They're both solids, okay? They're both white solids, powdery. There's the ammonium nitrate and there's the barium hydroxide. And I'm going to mix these two together. Hopefully I can get it all in there without spilling it. And put the top on because it generates ammonia, which stinks. And I'm just going to mix it around here. It's an unusual reaction in that it's two solids reacting with one another. Now, you don't see that very often because the point of contact between the two solids is very small. Two spheres touch each other at a point, whereas two gases can completely dissolve in one another, and so you get a lot more reaction going on. But in some cases, two solids will actually react with one another. So as this reaction proceeds, remember that we were releasing 2 moles of ammonia and 10 moles of water for every mole of barium hydroxide. Very endothermic. So I've got this little block of wood here with some water on it. I'm going to show you how endothermic it is by putting this, that's all mixed up. It's a nice slurry now because all that water has been released. And I'm going to stick it on that block, and I'll come back to that in a moment. I can show you just how endothermic this reaction really is. So what I'm claiming is that it's an endothermic reaction, but 3 moles are becoming 13 moles. That's a huge increase in entropy. These two things are solid, they're crystalline. The molecules in the atoms are held in very rigid formations. And there's not very many ways that you can arrange the molecules to get these substances, so the entropy is low. Whereas here we've got aqueous ammonia and liquid water. These molecules can go all over the place, and same with the aqueous barium ions and nitrate ions. So it's a huge increase in entropy, and that's why the reaction goes forth. If the entropy change was 0 or negative, the reaction wouldn't even happen. It wouldn't be spontaneous because the enthalpy is not favorable, and then the entropy wouldn't be favorable either, so you get a non-spontaneous change. This thing should be getting pretty cold by now. Not quite, yeah, it is there. So that block is, it's so cold that it froze the water that I sprayed onto the block, and that's actually frozen right onto the thing. Not gonna let go. That's when it'll break off. Actually, it's, oh, there. Yeah, so there's a little chunk of ice. I don't know if you can see it from where you are, but there's some ice on the bottom of this thing. So it actually took it down to below 0. It's so endothermic, plus 80 kilojoules per mole, and yet the reaction goes, and it does so because the entropy change is so large and positive.